This video is on the review of ideal gases, where we will apply the concepts of ideal gases to solve questions. In this question, the kinetic theory of gases is based on some simplifying assumptions. That the molecules of the gas are assumed to behave as hard elastic identical spheres. State the assumption about the ideal gases molecules based on number one, the nature of their movement. You must understand that the ideal gas molecule move in a random manner. So random motion or constant velocity until the molecules hit the wall or collide with other molecules where the velocity will change. Then in the second part, we will explain based on their volume. The total volume of the molecules is negligible compared to the volume of the containing vessel. In part B, a cube of volume V contains n molecules of an ideal gas. Each molecule has a component Cx of velocity normal to one side S of the cube, as shown in the diagram, figure 2.1. The pressure of the gas due to the component Cx is given by the expression PV equals to nmCx squared. M is the mass of one particle of the ideal gas, where m is the mass of a molecule. Explain how the expression leads to the relationship PV equals to 1/3 nm c squared, where c squared is the mean square speed of the molecules. You must mention that due to the large number of molecules undergoing random motion, there are two keywords here, large number of molecules, random motion, we can say on average Cx squared equals to Cy squared equals to Cz squared for all the molecules. Hence, C squared is equals to 3 times your Cx squared. So that means your Cx squared is equals to 1/3 of C squared. Then when you substitute your Cx squared equals to 1/3 C squared into this expression, we will get the answer that the one, which is 1/3 nm c squared. In part C, the molecules of an ideal gas has a root mean square speed of 520 meters per second at the temperature of 27 degrees Celsius. You must change 27 degrees Celsius to Kelvin. 27 degrees Celsius is the same as 273 plus 27. This will give you 300 Kelvin. That means the speed is 520 meters per second at 300 Kelvin. Then we want to find the RMS speed at the temperature 100 degrees Celsius, which is 373 Kelvin. The equation you use is half mc squared equals to 3/2 kT. Your m and k are constant. That means your C squared is directly proportional to the temperature in Kelvin. Or you can say that your root mean square speed is proportional to the square root of the temperature. So you can write down C RMS for 373 is divided by C RMS for 300 degrees Kelvin is equals to square root of 373 divided by square root of 300, this one. Then from there, the C RMS at 373 will be equals to 580 because it is square root of 373 divided by square root of 300 times 520. And this will give 580 meters per second.